Sure.
I've warned you now. All right, so I'm going to share my screen. You can see my screen, I hope.
Yep.
You can also open up your first aid if you prefer that to looking at the screen. We're going to start with some of these definitions down here, like preload, afterload, and then from there you go on to some of the graphs and then come on back. So first and foremost, what is preload in the understanding that they've taught you so far, or in the actual definition right in here? When I say preload, what comes to your brain?
What comes to mind, is the amount of blood that's in the ventricle to be ejected.
Exactly. So that's the actual definition, right? It's how much blood is in there. But there's really kind of two things that control preload. Okay. The big one is the one you already mentioned, the amount of fluid. Okay. But it's the amount of fluid that actually gets there. So there's two things here that are highlighted at the bottom that actually control preload. So you have venous tone and the volume. So preload is veins and volume. That's it. Any answer choice, anytime they're asking about preload, the only thing that is going to control it for our purposes, where everything's in a controlled little box for exams, is venous tone and volume. Okay, so give me an example of something that would increase our blood volume. It's
like IV fluids.
Like IV fluids, right? Okay, so then what would decrease your blood volume? Being stuck in a desert, right? Dehydration, right? Dehydration. There's only two ways to change the volume. You either have more or you have less. So IV fluids, you drank 2 liters of fluid, or to lower it, you're bleeding out or you dehydrated, right? All of that seems really, really obvious, but when it's in a graphical form, it's a little bit harder, right? So we're actually, have you looked at these graphs yet?
No, we haven't gotten to that quite yet.
Okay, so I'll lead this part. This is, you'll probably get to it tomorrow or the next day, or well, I know it's the weekend, but you know what I mean.
Yeah.
So this middle graph right here is all about preload. And when they teach you these 3 graphs, they do it in a really confusing way. So I like doing it with the definitions. Okay, so we're only looking at this middle graph here. And as you can see, on the y-axis, we have cardiac output or venous return. So either the amount of fluid coming in or the amount of fluid going out, because they should be the same, right? We know that really the venous return is our preload, right? And then down here on the x-axis, we have right atrial pressure or end diastolic volume. Okay, so this solid blue line is normal. So we have cardiac output this way, and we have our venous return this way. So as cardiac output is increasing, our venous return is going down that way. Nobody really cares about that intersection right there. What we care about is how you would increase it or how you would decrease it. How would you increase venous return?
Like constrict the veins?
Right. Constrict the veins, increase venous tone, or increase volume. So in other words, this line is saying increase your preload. Okay.
Got it.
In the same way, how would we decrease it? Dilate your veins.
Dilate the veins.
Or decrease your volume. You're stuck in a desert, your preload. So this is really a preload graph. Okay. So if we go down to where they explain it in words, we can go to this graph, this here, B.
I have one question. Why is it looking at right atrial pressure instead of like ventricular?
I believe we use right atrial pressure to measure our preload. We'll go back to that right now. So preload can be approximated by ventricular and diastolic volume, right? So how much is left after you filled. But the amount that's going into that filling is also in your right atria, right? You can't get to your ventricle without that. So, and that part I'm a little rusty on, so that might not even be true. But that's my understanding of it, okay?
Sounds good.
Okay, so this second graph is venous return. So tell me what it says. Read this part for me.
Changes in circulating volume or venous tone lead to altered right atrial pressure for a given cardiac output. Mean systemic pressure, the x-intercept, changes with volume or venous tone.
Okay, so our mean systemic pressure is this point right here. Okay. And again, they're saying that this end diastolic volume, the preload, is directly going to alter your right atrial pressure. So what you send out is what you get back in and all of that. It's a loop, right? That's why right here it says right atrial pressure or end diastolic volume. They're not going to be different because you're in that same loop. When we take this exam, we think about what's here, what's here. But remember that this is going through your body every second, every 60 seconds, you're going through the loop. So it's not going to actually change. When we're talking about a change, we're talking over minutes or hours, not over one cycle. So there shouldn't be a time when those two aren't agreeing.
So
Okay.
it's like even though the end diastolic volume, that's usually they're talking about the left ventricle, right? But whatever's in the
Yes.
right atria will end up there. So it doesn't matter.
Exactly, because this is the last place of your heart. This is the first place in your heart. So the only thing between them is arteries and veins. So yes, if you control or constrict or change those things, you'll change what's going to come to the right atria, but you're not going to change that in one loop. If you change those things, then you're going to have less in the end diastolic, and it's going to adjust the whole circuit. Okay, so things to know about this volume. It's preload, veins and volume. So if we're going to put one thing on our sticky notes, it would be preload equals veins and volume. Your mean systemic pressure, they could ask you that with right there. And then they give you the examples. So fluid infusion, that was your answer, right? That's how we would get this up higher to number 3. Or sympathetic activity. Why would sympathetic activity bring you up here?
Because that would constrict the veins.
That would constrict the veins. So we don't usually talk about constricting veins very much because we don't usually care too much. But when you talk about your beta 2 and stuff like that, like beta 2 is a sympathetic stimulator, and beta 2 is on your veins. So when you stimulate that, when you're running from there, you're gonna, constrict your whatever.
And also alpha 1, right?
And also alpha 1, because the alpha 1 works way more on your arteries than your veins.
Okay.
So alpha 1's never going to be the answer for veins. It's always going to be the answer for arteries. But yes, they're both there. Okay. And then for bringing it down, number 4, we have acute hemorrhage or being out in a desert and spinal anesthesia. So I don't know if you know anything about spinal anesthesia, but one of the side effects is that it dilates your veins a lot. In fact, people can like pass out or get really bad headaches or something like that because you can have a sudden drop in your venous tone.
Okay, wow. Okay. Yeah.
So all of that to say, back up to here, preload, veins, volume, and then you want to remember your EDV. Okay. Yes, I'm telling you right atria is the same as it, but that's not what the answer is going to be. The answer is going to be EDV.
Sounds good.
And then they also mention venous vasodilators like nitroglycerin. So that very specifically only affects your veins. And so that can drastically decrease your preload. Cool. So any questions about preload?
No, it all makes sense. So like with nitroglycerin dilating the veins, it stops, it slows the returning of the blood to the heart.
Absolutely. Well, it does slow the return. Yeah, you're going to because everything's going to be sitting in those veins. So have they talked about capacity at all yet or talked about like the storage of blood?
Not yet, but I think we're getting to it on Monday, yeah. So I'm happy to.
So they like to kind of mention that like your veins can actually store, I think, 3 times more than your arteries. Okay. So in theory, if you dilated your veins all the way, which your body would never do, you could keep all the blood in your veins, like a storage container, I think Sketchy uses like a vase, like a blue vase to describe your veins because it can just literally hold them. They're very floppy. They can get really big and they can store a lot. That's why people have all those varicose veins, all those ugly ones, because they get filled up and stretched out. And then the valves break and then they just stay blue. They stay filled with blood because your veins can just do that. So if you use a venous dilator or you decrease your preload a lot, in theory, you could do it enough so that none would get to your heart. Okay, and that's actually kind of how nitroglycerin works. It does dilate the vessels on your heart, but it also decreases the amount of blood that you need to that's coming to your heart and gives your heart a little bit of a break.
And the blood pools in the veins, right?
It pools in the veins, exactly. So you've heard that before. But that's what we call the capacity. The capacity is how much is being stored in your veins. Okay, so one little sentence here, but it's one of the three most important things about the heart. So you really want to be able to understand it and you want to have it memorized. If I say preload, you want to be able to say those three things, right? So what are the three things?
Veins, volume,
and EDV.
And EDV.
Okay, so you can kind of highlight the V in there for the third V.
Sounds good.
All right, none of that was rocket science. It's just something that you can kind of overlook or overcomplicate. Okay. Then we have afterload. So in your understanding, and again, I don't think you guys have gone through afterload much. What is afterload? What does it mean to you?
It's like the blood pressure, the forces resisting the blood being pushed out of the ventricle.
Absolutely. It's your blood pressure, right? The way I like to think about it really is just how big of the hole that your heart is pushing against. Okay. So in order for your, because it's load, it's weight. So it's how much, they're going to talk a lot about how it compares to muscles and how much weight you're lifting. That's very confusing to me. Okay.
Yeah.
So what is the valve that allows your blood to exit your heart?
Aortic valve.
Your aortic valve, right? So if your aortic valve is small, right? Let's say it's stenosed. Would it be easy or hard to pump blood through that?
Hard.
Hard. It's heavy. It is a huge afterload. It is going to be so difficult. And the most important thing to know about aortic stenosis is, in fact, that the afterload is massive. Okay. So what comes after the aortic valve?
The aorta.
The aorta. The thing about the aorta is, unless you have some sort of like congenital stenosis of it, it gets atherosclerotic, but it's so big and you don't really constrict or dilate it much. Okay. There's also
like
only
elastic,
one of
right?
them. Right.
Yeah.
So what artery after the aorta do we really care about when we're talking about blood pressure?
I'm not sure.
Okay, it's your arterioles. Okay. They're going to start making a really big deal about that. And the idea is you just have so many arterioles, and they also have really thick muscle that they can constrict really tight. Your arteries, you have some of them, but we don't really want to constrict those too much. They're more controlled by autoregulation, right? If you're running from a bear, we want to be able to say, okay, don't send blood to your kidneys, do send blood to your heart, do send blood to your lungs, maybe don't, but also send them to your muscles. We want to control and decide, because you have one big artery that goes to your kidney, just one. If you were to constrict that, that would be really bad. Okay, so think about arteries and your aorta as, even though this isn't technically true, is kind of, they don't really change that much. Okay, unless you have a disease or something that's actually like there holding it, no difference. The only thing that's going to matter is your arterioles. Okay, so if we're writing this out, we're going to say the afterload equals arterioles. Okay. And we're also going to say it's approximated by MAP, and the A, we're going to use that A in MAP. So let me open up a list here so that we can start. I don't want a new folder. I would like a list. And again, none of this is rocket science, but it's the things that you never want to get wrong on an exam. So preload. What did we say preload was?
Veins, volume, and EDV.
Perfect. And like you mentioned, it's specifically left. Okay. And now we said afterload is what?
Arterioles and MAP.
Absolutely. And we'll highlight our little mnemonic there, right? So as far as I'm concerned, that's half of understanding cardio. When you get those things down, you know, it helps a lot. Where first aid. Okay, cool. So Afterload is approximated by MAP. What does MAP stand for?
Mean arterial pressure.
Exactly. So the A in arterials is the same as the A in MAP. It just is literally saying arterials twice. It's saying the average arterial pressure is how you measure afterload. Therefore, arterials must be the most important thing, afterload. Okay.
Right.
Now we have this Laplace or Laplace or whatever, it's French law. Did you guys talk about this yet?
I think so, but I need some help.
That's fine. Okay, so it says if afterload is increasing, and how did we say we increased afterload?
The arterials.
The arterials, right?
Constricting
Our
them.
pressure is going to increase. So if you vasoconstrict, your blood pressure is going to increase, which is what you told me, right? When I said, what is afterload to you? You said, well, it's basically your blood pressure, okay? So these two things match. Then it says increase wall tension, okay? What that's basically saying is I told you that they like to describe this as weight, okay? So if I said you picked up more weight, your muscles had more tension, what would happen to your muscles as you lift up more and more weight every day? What's going to happen to your muscles a month from now if you lift up more and more weight?
Hypertrophy.
Hypertrophy. So this little law is just explaining that, hey, it's more work because the pressure is more, because we're more constricted. Therefore, we will hypertrophy. Okay, so that's Laplace's law. The way that shows is by this sentence here, which you can read for me.
Left ventricle compensates for increased afterload by thickening hypertrophy in order to decrease wall tension.
Right. So if we're constantly tensed and we're constantly being worked more, well, we'll just get bigger. And then it won't be so hard, right? Why would that be a problem? Why aren't we like, yay, awesome, you have a super muscular heart like we are when people are working out at the gym?
Because then it won't be able to hold as much volume.
Exactly, and that's going to affect our preload. Okay. That being said, if you're a healthy 25-year-old who runs marathons, who cares? Okay. Your heart is working great. It can hypertrophy. It can be really strong. And somebody who runs marathons, their heart is going to be bigger than a normal person. And we don't care. Okay. What happens though is when you're 80 and you've got all those varicose veins, right? So you already have all this venous backflow, not enough blood's getting to your heart. Then you're on blood pressure medicines, which are affecting your whole body. Your kidneys aren't working great. And then you get aortic stenosis. Okay. And like I said, aortic stenosis is one of the parts that can control afterload because it is something that can stenose. It's before the arterioles. So we'll actually add aorta to this list. But when we say aorta, we really mean aortic valve. So we'll do that. Okay. So those are our 3 A's. So then you have a big heart, messed up preload, and you have high pressure, and that's how you get heart failure. Okay, so young person, no problem, a little bit of hypertrophy. Old person, that's heart failure. Okay, so let's go back to the graphs now. And again, these are some of the most complicated graphs they're going to teach you, and I don't think they're that bad when you really break them down like this. So we want to go to total peripheral resistance, this third one. So when we talk about total peripheral resistance, it's the same thing as blood pressure. It's the same thing as SVR, systemic vascular resistance, and it's the same thing as arterioles. So we're going to do that here. Pressure equals total peripheral resistance, identical to systemic vascular resistance, identical once again to our arterioles.
Yeah, thank you, because I was confused if those were different or not.
They're not. Okay, technically, are they going to be like a different formula that gives you a different specific number? Sure. But in how the body works with them as a doctor instead of like a physicist, they're all the same. Okay, which also means that these correlate strongly with afterload. Okay. But there is a little bit more that plays with pressure, but for the most part, we can kind of say that these coordinate as kind of a subset of afterload. Okay, and that's because resistance has to do with how constricted you are. resistance, these two are the same. And when they talk about vascular, they're really just talking about, again, the most important one, arterioles, because we don't care about veins, we don't care about arteries. They have nothing to do with your blood pressure for us. Okay, so we're going to look at the graph. So this third graph has a few more lines, but we're going to ignore a couple of them. Okay, so what were the blue veins here? The blue lines here?
They're increasing or decreasing preload.
Exactly. That's what they are here as well. Okay, no difference. What you'll notice though is they kind of come to a head here instead of being spread out. So it's a different graph when you see it come to a peak versus when you see them come here. Okay. Now, what was the red line here, labeled in red here?
Cardiac output.
Cardiac output. So same thing, red line here, and it's actually the same shape. It goes up and over. Okay, up and over. Kind of that hyperbolic KM line that you learned, where you get to kind of like a Vmax or whatever, because your cardiac output can only go so high, and that's just it. Okay, so when we're looking at what will increase your cardiac output, and we're talking about afterload, if I want to get more blood out, do I want increased afterload or decreased afterload?
Decrease.
Right. And we just said that afterload, TPR, resistance, if you want to get more out, you need less resistance. So these ones are inversely related versus these ones, which were kind of directly related. So that's when you start getting confusing. You're like, wait, it goes up when you go down. But if you understand that cardiac output, and this is just how tight your arteries are, you're going to be fine. Same thing here. You just drop it with total peripheral resistance. Okay. But we said everything was in a circuit. So these are also going to affect your veins. Okay. Because if you don't get as much blood through your arteries, how are you going to get blood to your veins?
Right.
Okay. It's all a loop. But when we're looking at these graphs, we're trying to isolate one or two things because really it's all connected, right? None of these graphs on you could ever exist. This is if we took one thing and isolated it and learned what a graph it would be for education. So that's where the heart gets really confusing, because you'll sit there and be like, okay, yeah, but this connects to this, connects to this, connects to this, so that can't be the answer. No, they're asking you about step one thing, because all the way down, it's not real. Okay, so let's read what it has here for total peripheral resistance.
So at a given mean systemic pressure and right atrial pressure, changes in total peripheral resistance lead to altered cardiac output. Okay,
so if we change the resistance, we will change the cardiac output. That's all. Okay. And then the examples they give are vasopressors, that's to vasodilate, that's to decrease our TPR right here. Or to increase our TPR, exercise or an AV shunt. You guys weren't really talking about AV shunts yet. That's a little more advanced for you. Right now, just think exercise, catecholamines, whatever. Okay. So this kind of note down here explains what I was just talking about. Changes often occur in tandem together. They may be reinforcing, like exercise can increase entropy, can decrease total peripheral resistance, or you can have compensatory heart failure, and all these things can happen at once. So what it's saying is these things really all happen together. We're just going to talk about one or two examples. Okay. Any questions on that?
No.
Okay, so now we're going to look at their examples for afterload here. So arterial vasodilators decrease afterloads. Okay, you guys haven't talked about ACE inhibitors yet, right?
Not yet.
Okay, so not important. They're a medication. They decrease preload and afterload. They do that by decreasing the volume you have in your body, preload, and by also vasodilating, right? That's a perfect drug because it decreases it kind of the pressure from both sides. Decreases your preload, decreases your afterload. Beautiful. Okay. We also talked about with Laplace's law, if you have chronic hypertension, chronic high arterial pressure, you're going to have left wall hypertrophy. okay, which could be fine, could also be really bad if you have heart failure. Okay, so back to our little list here: preload, veins, volume, EDV; afterload, arterioles, map, aortic valve, which also plays closely with our resistances and our pressure.
Right.
So we understand and can control a lot more of this part than this part. Most blood pressure drugs work here. They're vasodilators.
Mm-hmm.
But if we can, we'll also work on this part. Okay, so now
Is
we
there
have
like a different, like, is there a different time course? Like, are like the venous dilators faster or slower or anything like that?
venous dilators do work super, super fast. And they're usually only used in emergencies. So nitroglycerin, the example they used, has a lot of side effects, and we usually only use it when you're having chest pain or a heart attack. It's only given to people if you're having chest pain, which we call angina, or a heart attack. That's it. The other venodilators are only used for hypertensive emergency. So that means when your blood pressure is so high that it's causing organ damage. Because if you vasodilate those veins, it's going to have a much bigger effect than just vasodilating your arteries a little bit. And so your artery vasodilators are first line. Things that decrease your volume are also first line, but we don't really use venodilators unless you're having a heart problem or you're in hypertensive emergency. I'm sure there's some exception that a doctor would listen to this and be like, well, you forgot about. But for the drugs you're going to learn, the emergency ones work on veins, and sometimes arteries combined. You're never going to do veins otherwise.
And the maintenance ones work on arteries.
Arteries or volume, right? So a lot of times we put people on diuretics just to make them get rid of some fluid, because that's like really easy to do. But our most common blood pressure medicines, like metoprolol, are beta blockers. They work mostly on your arteries, or also maybe your heart rate. But we use like sometimes vessel specific ones or heart specific ones, which you did learn a little bit about in
a little bit. Yeah, there's the like
in your FTM. Exactly. Okay, so you have stroke volume, which isn't really, is kind of uses both afterload and preload in it. You can't really understand stroke volume until you understand these two. Okay. Contractility has a huge explanation here, which has nothing to do with what contractility is. This is talking about how skeletal muscle works. So you remember for MSK, you had that like cartoon of how skeletal muscle, and you have the sliding, and you have your like H zone and all. Cardiac muscle doesn't really work that way. This is the only explanation in your first aid about how cardiac muscle works. Okay. The big important thing is that it has to do with intracellular calcium. Okay. All of this to just say, hey, you have more calcium in there, you have more contractility. Okay. There's also some examples of things that increase or decrease it, but that's basically how strong that contraction is. Not how much fluid you have, not how the vessels are. The only thing that affects contractility is like calcium or things that affect calcium, right? Like this is a calcium channel blocker. That's a medication we use.
Like verapamil or something.
Exactly. Okay. Acidosis affects calcium. Hypoxia, hypercapnia affects calcium, and also affects the muscle itself. So you'll have to kind of memorize this pathway, but it's really just about the muscle. It doesn't play as much role with that. So let's talk about stroke volume. Do you know what stroke volume is?
It's end diastolic volume minus end systolic volume, so the amount of blood ejected.
Great. So you have a formula for me, right? It's how much fluid actually goes out. So afterload is how hard it is to get that out. Preload is how much comes in, and stroke volume is just how it comes out. So as you can see, this is directly controlled by preload, afterload, contractility. Okay, so it makes sense that if it's really hard to get the fluid out, you're going to have a smaller stroke volume. If you have a lot of fluid, you'll have a bigger stroke volume. And if your heart is really strong, you'll be able to get a lot of fluid out. Okay. Conversely, if you have heart failure, your heart is a pump, right? If the pump doesn't work, your stroke volume will not be good. Okay. How is that different than ejection fraction? Because kind of sounds the same to me.
Ejection fraction is the proportion of blood that's in the ventricle that goes out.
Right. So it kind of takes into account preload. It's like, okay, but like, stroke volume is saying, or ejection fraction is saying you got 1/3 of the blood out. Okay. It's instead of just saying, oh, well, like stroke volume, if you're dehydrated, your stroke volume goes down. That doesn't actually say how good your heart's working. Right? Stroke volume is just saying it's getting out 1 liter or 5 liters or whatever, but it's controlled by all these things. Ejection fraction says, okay, I don't care about the whole system. Is the heart working? Okay. And how I do that is by saying, all right, you have plenty of blood or you don't have plenty of blood. I don't care. You're putting out 1/3 of it.
So can you tell me about something that would affect ejection fraction, but not like stroke volume? Is that a thing?
Oh, that's a really good question. Yeah. So the example I just gave, if you have dehydration, right, you're going to have a low stroke volume. But you, healthy man with a good heart, are still going to be able to get 2/3 of that blood out. Your ejection fraction is going to be the same in theory. Okay.
So it's like something that would only affect preload, for example.
Exactly. Something that would only affect preload. Because ejection fraction really has to do with your contractility, how much it can actually get out of there and how. So in the example that really affects ejection fraction, and the only reason you're learning this is because of heart failure. We define heart failure by your ejection fraction. Once you get to a certain percent, a fraction, we call it heart failure. Okay, so this whole phrase, this whole formula, we only use it for heart failure, in real life. So we say you can either have a preserved ejection fraction or you can have a decreased ejection fraction. That all has to do with how much contractility. So if you read this sentence,
left ventricular ejection fraction is an index of ventricular contractility.
Right. So what we really want to put over here, if we're adding contractility equals calcium equals ejection fraction. And other things, but everything affects everything, which is kind of the problem. But okay. You won't really talk about oxygen demand. That also just kind of makes sense. If you're working harder, oxygen is your fuel. Okay, so if you would use more fuel, you would use more oxygen. You're stronger. The weight is heavier. You're faster. It's bigger. You need more oxygen. Okay, the problem is all of these things kind of go up or down with heart failure, and that also plays with wall stress, which you'll talk about more of the places and everything, the pluses. Okay, so we went through everything on this page, right?
Yes.
Okay, so we're going to go down to that last graph over here, which is our word inotropy. So what is inotropy?
Increased contractility, calcium.
Exactly, inotropy. So no nice mnemonic for contractility. There's no like letters that go together like the preload and afterload, but the word inotropy literally is the definition of contractility. These two things are just related. Okay. So if we want to increase inotropy, if we want to increase contractility, how would we do that?
Sympathetics or.
Great, perfect. Yeah. That's their first example, right? Mm-hmm. Catecholamines. There's also some drugs, exercise. Okay. How would we decrease contractility?
Like a beta blocker.
Perfect.
Yeah.
Okay. Heart failure, narcotic overdose, or sympathetic inhibition. Sympathetic inhibition is beta blockers. Okay, so I messed up a little bit, so we're going to go back because I'm just realizing it now. So we should have done these two graphs first, because as you can see, this one is controlling the red line, the cardiac output. Okay. This one is saying you're changing this intersection. So you see this black dot in the middle? When you change TPR, you're changing preload and afterload. So you're changing where the intersection is. It's all about the intersection. This one changes just the red line.
I see. So wait, which one changes both? Like what's the
TPR.
third graph? Okay.
Because we're changing how much is getting to the veins, getting to the arteries. So we talked about that, but then I used the wrong line. This red line, the cardiac output, is directly controlled by the inotropy. This one is going to change the red and the blue line. So this arrow going from here to here is saying we're going to use this blue line and we're going to use this red line. So two things change with TPR. One thing's change with preload, one thing changes with inotropy.
Okay, so TPR is associated with afterload, but it's still
but it still shifts the preload because the circuit. Okay. The examples, we read that. Changes in contractility alter cardiac output for a given right atrial pressure preload. For a given right atrial pressure, saying without changing the preload. So you're going to stay along that line. Okay, that's all three of these. So these are worth memorizing. These two are the simpler ones. You start with these, you practice these, you're able to recognize it, and then you're able to go up and down from the different intersections. So a question will actually say, a patient is running from a bear. Which lines? And you'll have to say either up or over, and they'll have different black dots. You'll see that in Modo. They'll, I could even actually pull up the Modo. Hold on.
Yeah, I got to do a lot of it today, so.
Do you have it up?
Yeah, I can get in 1 sec.
Okay, there.
Okay.
Oh, you can't see my screen.
No, I can see it.
You can see the Modo?
Yeah.
Okay. All right, so I'm just going to scroll until I see one of those graphs. There should be one. There should be a couple. This is one of them. Here's one. Okay. So first thing we want to do is check our axes and make sure they didn't flip them, right? So cardiac output is still here. Right atrial pressure is here. And notice it says right atrial pressure or end diastolic volume because we talked about they're pretty much going to be equivalent. Okay. So this solid line here is our cardiac output. Nice and labeled, right?
Mm-hmm.
Okay. So the changes indicated by the dashed line. So here's our venous return. Now it's in higher. What would cause that? We'll flip back for a second. So we're looking at this graph, right? Mm-hmm. We have one here, and then we have this line that's moved up. So we need something that does this.
Okay, let me see the choices again.
Absolutely.
E?
Increase contractility. So why would contractility, I mean, yes, it does, but I don't know if contractility would be our most direct answer.
So C would be the right one then, right?
So that would be, so I want to choose something with veins or with volume. Those still might be the answers because I'd have to think through them. But if I'm seeing a graph that's saying my venous return is increasing, the first thing I want to go through is the answers that have something to do with venous or volume.
I was just confused because both B and D talk about decreased venous return, but I would expect from this graph for it to be increased. So I must be getting confused somewhere.
No, I think you're doing right, but that's what I'm saying is we want to just identify that first, right? So you're right. To go up, we would need one of those. So pull up the answer key if you have it.
What's
Because
the
I don't want
question
to tell you
number?
the wrong thing. 170.
Okay. One second.
I would be more tempted to go with C because we talked about how TPR affects veins and arteries.
Wait, I think I have a different
A
version.
different one.
downloaded.
Hold on, let me get it then.
Sorry.
No, you're good. Moto CV.
Just real quick on your schedule, I guess these are the question numbers you were. I mean, I have to do all of them by the end, right? So
I
there's
don't
no-
know which ones I have, to be perfectly honest. This should have the answers. It says A on it, right?
Mhm.
But it doesn't.
Well, I think there's a version A and B, and then there's answer documents for those.
Oh, thank you. It's been so long. I don't see it. You don't have the answers? Well, can you go to look what the similar question would be? Just look for this graph.
Yeah.
Should be C. Because we're also increasing the cardiac output. We're going from that line to that line, even though we're not going up that way.
Let me see. I think I'm about to. Yes, it was C.
Okay, perfect. So let's do the next one. So the dashed line in the figure. So what's changing this time? Is our venous return changing?
No, it's decreased cardiac output. Oh wait, no, increased.
Because we're going to the dotted line. So we're
It's
increasing our
increasing cardiac output.
Okay. So how would we increase our cardiac output? Would we increase our TPR?
No.
No, that would decrease. It'd make it harder.
Increased
What about
contractility.
increased contractility? Exactly. Okay. So we're just going up in cardiac output. It's going to be increased. Could increased blood volume downstream make us have increased cardiac output? Yes. And that's why these get hard, because you can talk yourself into B, but it's not the best answer.
Well, it's like, yeah, it's like you were telling me these things all affect each other. So I
They
have to
all
learn
affect
to
each other. Now, what's the
associate
difference
right thing.
between A and E?
Okay. For this purpose, I would say they're the same.
For this purpose, they're exactly the same. Okay. What's wrong with D?
That would go the other way. That would shift the graph.
That would be the opposite. So we know that we're dealing with this graph, this line here. We know that we're dealing with this one. We're looking at these red lines going up or down, inotropy. And we know that inotropy has to do with our contractility.
Right.
Versus this one, which we had just did, where we were dealing with the blue lines going up or down, where we needed something there. But since we kind of went up on both, we had a TPR, which wasn't ideal. So that was a harder question than this one.
Can you return to the previous one really quick?
Of course.
So the explanation was that increasing the systemic pressure would increase venous return. Okay.
Because there's not a better answer, right? In this one, I said, let's look at the vein ones first, but they were both directly wrong, right? They would both directly decrease it. And I know that contractility isn't going to affect that line at all. Contractility is just that first graph.
Right.
So we had to go with our TPR one. Okay, so here's one of the harder ones where I'm telling you that all the intersections matter, right? So we're looking at this one where we're looking at these intersections. And those intersections are called mean systemic pressure, I think. Again, it's all a little fuzzy. Okay, so remind me which ones are blue lines and which ones are red lines, since everything's black and white here.
The blue lines are the ones that shift vertically up and down.
Okay, these
So
perfect.
like, yeah.
And
then
you'll
the red line-
notice some of those intersect, some of them don't. So we know when they intersect, which graph we'll be looking at
when they intersect,
of those three.
TPR.
TPR. So when we see those intersections where the ending points don't change, that's when we're talking about TPR. Versus here, we're not talking about TPR. So that alone actually gives you a hint about what's going on with each one. Okay, and then these lines here are cardiac output or red lines.
Okay, and those go left and right, I guess.
Right, so they're going to give us our first example. So a cardiac function, venous function curves were generated. Who cares? Starting from the control point, labeled control, what would happen if you gave a person saline? So close your eyes and tell me, of the three graphs that we're talking about, the first one with the red, second one with the blue, and the third one with the intersection, if we're giving saline, which one of those graphs is affected?
The second one, the volume.
Right, the blue. We're looking at the blue lines, the volumes, the preload. Okay, and so what would happen if we
You're increasing preload.
you're increasing preload? So where would we go in this? Would you go to what would be your options?
I would think to go vertically up.
Okay.
Oh, wait. Yeah.
So we'd either be dealing with C or E, right? Because those are both up, or B. B is also up. Okay, but what we don't want to do is change the cardiac output, because if you looked here,
I would say E then, right?
Right, we don't want to change this line. We only want to change this line. So if we look, we want to stay along that same red line, which is D to control to E, and we want to increase. And notice we're on the line that doesn't have the shared peak because we didn't change TPR. We just gave them some fluid. So if you look at your answer key, the answer should be E, because we didn't change the red line. We stayed with the red line and we increased the blue line.
Okay, so I see. So when they tested, they put all three, they picked that third graph as everything.
They always do, because that's the hardest. But if you can break it down, if you can say, all right, which of the three am I looking for? It's much easier, because they don't teach it really like that. They throw everything together and it's very confusing. So you want to be able to isolate it and then go from there. Okay.
Wait, I'm sorry. So something that increased contractility alone would take you to B?
Yes, because we're staying on the same preload line and just jumping up on the red line. And I'm just going to use the colors because that's the easiest way to describe it. So what if we change TPR? If we decrease TPR, where would we go?
A? No.
Remember, that's inversely related for TPR. So we actually go up here.
I see.
So
TPR, which is associated
this is the control line. And if we decrease TPR, we go up to the next intersection, where we change the red line and we change the blue line.
Okay. And they would talk about, what would they talk about that?
Well, let's look at the next question, shall we? Okay, so a patient is doing exercise testing. The control represents baseline cardiac. Okay. During treadmill, there will be a shift from resting to which of the following points? Okay, so
you know contractility will go up.
We know contractility would go up, so that bumps us from this DCE line to the ABC line. So we know we're along here. Okay, what would happen to preload?
That would increase as well.
Probably.
So then it would be C.
It would be C. Well, no. Yeah. Because we'd be increasing and we'd go up there. And I think exercise is on this list. So let's see. Exercise 6.
So exercise decreases CPR, okay, which moves to the next higher up intersection, I guess.
Exactly. So you're changing both lines. And that's how these get really complicated and really convoluted and everything. So, but you're doing good. You're doing great for never seeing these before. And I just taught them to you, and now you're getting answers right. These are some of the hardest ones on the exam, and that's why I wanted to do them with you.
Well, thank you.
All right. So treadmill, everything goes up. No problem. And that's all that they have here on Moto. So there's also not a lot of practice problems for them. One other way we can look at this. Are you tired? Do you want to keep going?
No, let's go.
Okay. One other way we like looking at afterload and preload is when we talk about murmurs. Have you guys done murmurs yet?
Yes.
Okay. Oh, this version doesn't have it, does it?
Which page are you looking for?
I'm looking for the picture that shows the visual representation of the murmurs flow volume loop.
Ooh, I can just think, is it 291 or that's something else? That's like the sound, right?
Can you share your screen? Do you have it up?
Yeah, I don't think it's the right one, but here, let me show you.
All right, let me stop and you can do it.
Oh, it says host disabled.
Oh, I have to give you permission. Share screen, go ahead.
Oh, I have to change my privacy settings. 1 second.
The problem is I only have my 2018 on here. Let me see if I have a 2019 or 2021 somewhere. Mm, 21.
Oh, it'll only let me do if I quit and reopen. I'm sorry, but
I might be
so I
able to
don't
find it
wanna
on
do that.
Google. Hold on. Murmur flow volume loop. Yeah, I can do it this way.
Okay.
So find this in your first aid, the pictures that look like this.
Oh, that. Okay. My bad.
Okay, so we can go to
Okay.
the normal one first because I do have that. So, okay, if we're looking at this guy, right? So this is another visual representation of afterload, preload, contractility, all those things, right? So when we're looking at these things, our height is our afterload. Okay, it's the left ventricular pressure because you told me afterload was how much pressure we got. Okay, this one says volume. So what do you think the width is going to be?
Preload.
Preload. Okay, so as far as we're concerned, height is afterload, width is preload. Okay, so if I look at something like aortic stenosis, you'll notice it's super, super tall because of a lot of afterload.
Grace, I learned this like 5 minutes ago. So, but right?
Perfect,
Because
right? So
you need
the
higher
height,
pressure to open the aortic valve, right?
exactly. And you can reason that through and you can think about it, or you can just say, hey, look, that's a lot of afterload. That's a lot of pressure. And if that valve is very small, how much fluid am I really getting out? Okay, because this width is also your stroke volume. Okay, so if I were to ask you, what is the stroke volume in somebody with aortic stenosis, you'd be able to tell me low.
Yeah.
Okay, and one of the things you'll notice is with all the stenoses, your stroke volume is low because it's a stenosis. You can't get fluid out.
Right.
So we can look at, I want to look at the other stenosis.
Mitral.
This one. Okay, you'll notice that the volume is lower here and that the stroke volume, the actual width, is actually smaller. Okay, there's not a big height difference because the only things that affect your afterload are the aortic valve and your arterioles. The mitral valve really doesn't. That's in the heart. That's before your afterload. So it's not
Right.
really going to change. Okay. It's just you have a problem getting it out. So if I were to say, which two murmurs have decreased stroke volumes, you would now tell me.
Mitral stenosis and aortic stenosis.
Exactly. The stenosis is. Stenosis means I can't get stuff out. Okay. So now let's look at regurgitation. What do you notice about the preload, the volume?
It's greater.
It's super great. How big is the stroke volume?
It's greater.
It's big, right? So if I were to say which murmur has a really big preload or a really big stroke volume?
Mitral regurgitation.
Mitral regurgitation. How do you think a patient with a lot of preload is going to present?
Heart failure.
Heart failure, swollen. These are the people where you're going to look at their ankles and they're going to be balloons because they have so much extra vein dilation and volume. Your preload is big. How's your afterload?
It's normal.
It's normal because your mitral valve is before your
It's within your
afterload.
heart. Yeah.
If anything, it's just a little bit decreased because you have everything stored and you can't really get it there. But it's not drastic. Okay. What about aortic regurg? How's our preload?
It's high.
High, almost 200. Okay. How's our stroke volume?
It's high, very high.
Very high. So if I were to say which two murmurs have high stroke volume, you would say
mitral and aortic regurgitations.
And which ones have low stroke volume? The stenosis.
Stenosis.
So it's not that much. Now, is our afterload kind of increased here a little bit?
Yes.
Right.
Because it's the aorta.
It's the aorta. It's involved, right? It's not going to be crazy high, but we're still going to have issues because if the valve's not working, we're just going to have issues. So you can memorize a lot of, things about these pictures. But as far as I'm concerned, the tall one is aortic stenosis and the wide ones are the regurges. And also aortic stenosis kind of looks like an A.
Oh, wow.
I need to draw an A over that one.
Yeah, because I was following your schedule. So I watched these murmur videos before everything started. And I was like, damn, I don't understand anything. But now it's clicking.
Right. And do you want to take it one step further? Okay. Let's see this. I love this stuff. Aortic stenosis, wiggers, right? Because you probably had some scary wiggers today. Okay. Oh, no. What do you notice about this one? It's tall.
The pressure is high.
Pressure is taller, right? Once again, our afterload, our pressure is high with aortic stenosis because this is really the same graph as this one. You can see they're shaped the same. Okay. They're just looking at slightly different things. The normal is not going to have you way up here.
Right.
So you can see that similarity. I don't think the 2021 or whatever versions newer does a better job at showing the murmurs with those, and they have them next to each other. But the 2018 doesn't, and that's the only bad thing.
Send you a screenshot of that?
Yes, could you?
Right. Yeah. I'll text it to you.
Yeah, that's perfect. And then I can just pull it up on my screen. I just got it. I'm just going to send it to my email real quick so I can open it because I don't have a Mac.
Or did you want me to send it in Zoom or you got it?
No, I got it. It just has to come up now. From me. Nope, that's not. Here we go. Okay. Here we go. So yeah, you can see the similarities in these two, right? Okay, they're both taller because they both have increased afterload. So here's some things we see here. We're going to see decreased stroke volume. right? We said it was really skinny. We said we're going to see increased left ventricular pressure, really high pressure. And our end systolic volume is going to be increased. No change in end diastolic volume. Why do you think that is?
Because it's not affecting. Hold on. Wait, let me think.
Well, tell me what end diastolic volume stood for again. Was it afterload or preload?
Preload.
Preload, right? And this line right here is our preload, right? It's about 175 right here, right? We haven't gotten up to that 200. Right, we can see this one, the preload's 250 here, right? So it's normal here because it's not a vein or a volume
because
problem.
it's not affecting the yeah, okay.
And it's getting out eventually and getting back, but our stroke volume is still decreased. So this is an example where your preload is fine, but your ejection fraction would be messed up. Okay, and this one is going to get ventricular hypertrophy, and this is going to be one where you get a really big heart, lots of heavy weight, really big heart. Okay, we can see for this mitral regurg, we have our wide one, right?
Mm-hmm.
And you get this kind of backflow here, the tall V wave. No one's going to, like, the answer is not going to be tall V wave. They're going to show you this and you're going to have to say it's that. Aortic regurg, large pulse pressure.
I'm sorry, can you go back to the previous one and just talk me through real quick?
Yeah, let me go to the original one with labeled. 1 second, because it's not something I've done in a while. So if we're looking here, right? This is the graph that we're looking at. So your mitral valve closes here and it opens here. Okay. So if is mitral regurg, is that the one we were looking at? Mitral regurg?
Yes.
Okay.
Mm-hmm.
Is mitral regurg a problem with the valve opening or a problem with the valve closing?
Closing.
Closing. So we should have some issues here.
I see.
Same thing, the aortic valves are a top. I say aortic a top because then I can remember that the A's are up high. We're going to see this top line affected with the aortic murmurs. We're going to see these bottom lines affected with the mitral murmurs. So aortic a top. So if we go back to that picture, mitral regurg. So I can't explain why. Because it's on this side. So it kind of backflows. And that's all I can tell you. And Jason Ryan will have to do the rest because I don't remember the rest.
Okay.
We
love Jason.
Yes, right. And then mitral stenosis, you have this really high pressure here. So this one's pushed all the way up. So the same way that your aortic stenosis is pushed way up with that stenosis, with mitral stenosis, you have the bottom line pushed up.
Which is atrial pressure?
Yeah.
Okay, because it can't get from the atria to the ventricles.
Exactly. And then you'll notice they have the things like the stroke volume listed for each one of these, which you already know. They'll also have the end diastolic volume, which you already know because it's just preload. And we said that the wide ones were the regurges, and they'll have increased end diastolic volume, and the stenosis as well.
Awesome.
And I think that's probably more than enough for right now. Those are some, that's why you have to understand afterload and preload, is because they're going to test it to you in test it on heart failures. They're going to test it on grafts. They're going to test it with heart murmurs. They're going to use it as descriptors for everything.
Yeah, thank you so much. It's been, extremely helpful. Thanks for